So when we talk about the subject of thermodynamics, immediately comes to mind the idea of an engine. And so this is a picture of the Maid of the Lock steam engine ship that's still in operation as far as I know. And steam engines are more of a novelty now because, they're not very efficient. They were the first kinds of engines that we dealt with, and they did great, for the period that they have them. The efficiency is very low for them, but they, enabled us to do things we never could do before. And so, in this clip that I like to show, there's a computer animation of this steam engine, of this ship. And one of the things that it shows inside there is a piston, and inside there's actually two pistons. There's one above the other. What happens is, well, these are cylinders, and here's the piston. What happens is this gas comes inside, and when the gas is inside, this is the hot steam that's inside, so you could burn coal or whatever, and then as you burn that, you can heat up water. Water turns into steam, and you bring the steam in here. And it's ducted through in a specific way with this. And then what happens is this piston moves this direction. And as it does, it's moving cranks and then eventually moves the paddle of the ship. But this hot steam pushes it this way, so it's doing work on it. Now as it expands, this steam inside cools down, and then by the time it gets way over here, by the time this piston is over here, this gas inside here is cool. And then what happens is that you put more hot steam in here, and when you put hot steam in here, this pushes it back the other way, pushing this out the exhaust, and then this does the work and pushes it this way. And so it goes back and forth, back and forth, back and forth, and then turns the the crankshaft for the ship, and then eventually the pedals of the ship underneath. Another picture of this would be like with a train, pushing the lever back and forth on the train, making the wheels go forward. And so that's the basic idea of a steam engine. And really the basic structure of engines are dealing with that. We have gases that are expanding that can do practical work, and that's essentially the core of thermodynamics. You've probably seen steam stacks like this, where we produce electricity. We're heating up water, which turns into steam. That steam turns a turbine. Then that turbine turns a generator, produces electricity. Over on the right-hand side, you have a picture of a train. And, the hot steam is pushing the pistons, back and forth, and, pushing the train forward. And so, you see those older movies where you have trains like that, and it really transformed life, or transformed our lives, the invention of the engine. And so the study of thermodynamics is that we can take thermal energy and transfer it into mechanical, actually practical work. And so all types of combustion engines, we're dealing with this, electricity production. So a huge deal here. Now, when we consider a thermodynamic system, we want to consider the system itself. And so this is the gas inside a container or a cylinder or whatever. We have a boundary around the system, and then we have the environment surrounding the system. And so for our system, we're going to be dealing again with ideal gases like the last unit, and considering the gas inside as an ideal gas. The boundary itself controls how the environment affects the system. So if you have an insulating type boundary, the system is going to be insulated inside and not affected as much. But if you have a very conductive boundary, then it can be pretty high, or the thermal interactivity can be pretty high. And so if the boundary is closed to mass, it means that mass cannot get in or out. And so with an open system, mass can enter or leave, but a closed system, mass cannot enter or leave. If the boundary is closed to energy, then we actually consider it an isolated system. And so these are the three types of systems we'll be dealing with here. So if we consider the Earth as a system, we could talk about what kind of boundary it has. And so if we consider that, the energy can be transferred in, right? So we get energy from the sun. So in that case, right, we're receiving energy. We're not an isolated system. The question is, are we closed or open? And so it depends on how technical you want to be, right? Because technically, sure, we lose some mass, we gain some mass, but it's not on a very large scale. And so, you could probably argue either way there, right? All right, so in the thermodynamic process, we can be changing the pressure, temperature, or volume. And then, if we're looking at that, the gas itself can be doing work, or work could be be done on a gas. And so we have both of those situations in a thermodynamic process. If we consider back to our steam engine, right, we have that gas that's expanding and it's pushing that piston over. As it does, it's actually doing work as it does that. So, if we have a frictionless cylinder here with the piston, the piston can be moved up and down, so work is done on the piston, and so the gas can also do work on the environment. So this this idea of using this cylinder with a piston that can move up and down is a really helpful example that we use pretty extensively here in thermodynamics to evaluate what's going on with the gas and how it's affecting the environment, or the environment's affecting the system. Now, if we consider this gas inside, and let's say we have a certain force that's bringing this piston down like this, right, over a certain distance. Well, if we multiply and we look at work, right, work is force times displacement. If we multiply area over area, which is essentially 1, right? So this area right here, the area of the piston, area over area, we know that force over area is pressure, right? So however much force over that area is going to be a certain amount of pressure. And then D times A, right? If we take the area times the distance here, we actually get the volume, right? And so what we can get here is, with work, we multiply the pressure times the volume, and that will give us, how much work is done on the gas or by the gas, depending on which way it's going. So if we draw that out, right, we can put this on the side, and let's say that the gas is doing work. So what happens when the gas does work is that the volume expands. And with that volume expansion, we, delta V there, we have a certain amount of pressure times the change in volume, and we can figure out, the work done by the gas. And in this case, the positive volume change means that we'll have positive work. Now, if we have work done on a gas, that means that the volume is getting smaller. And if the volume gets smaller, work done on the gas, we'll have a negative, it'll be negative. So the change in volume is negative, and we have that. So let's go ahead and take a look at this with M1. Calculate the work done by a gas that expands from 0.02 meters cubed to 0.8 meters cubed at standard atmospheric pressure. So yeah, go ahead and try this one here. Go ahead and pause the clip. You're using pressure in pascals here, so we want to do that. And so yeah, go ahead and try that, and when you're ready to check, you can hit play to continue. All right, so the the volume is expanding here. We have the constant pressure, 101,000 pascals times the change in volume. So it's going to be positive work. The gas itself is doing work, going, the volume is increasing, so this would be 78,780 joules.